The University of North Carolina at Chapel Hill and Cisco are developing a telepresence video wall system for enabling informal conversations between remote coworkers. In this project, 2 video walls have been constructed at UNC. Each video wall consists of 4 large screen displays and a teleconference audio system. Eye contact is facilitated by switching between 2 sets of cameras as people approach the displays to speak with one another. The first set of panoramic cameras captures a wide-angle overview of the room, while a second pair of personal cameras captures people at eye level to better facilitate eye contact during conversations. Image segmentation is employed during the switching process to remove distracting duplicate image artifacts that occur when a person or object is seen by more than one camera. The UNC-Cisco group has implemented an image matting refinement step for increasing image quality along the edges of segmented people and objects during conversations. Image matting algorithms are effective for extracting foreground objects from still images or video sequences, but require a correct set of labeled pixels at each frame, which can be difficult to obtain in practice. The team's offline image segmentation algorithm uses 2 image matting methods, Bayesian matting and closed-form matting, for computing optimum edges around segmented foreground participants. Images from multiple Connect depth cameras are thresholded to create a 3-channel trimap image that guides the segmentation process. Image pixels that are closer than a comfortable speaking distance of 1.5 meters from the camera are labeled as known foreground. Pixels farther than this distance are labeled as known background, and an expanded group of pixels along the border of the foreground silhouette is labeled as a boundary region. The color and opacity of this boundary region can then be either estimated from nearby pixels or computed given a global optimization function that further enforces smoothness along edges. In the past, the team's segmentation algorithm relied exclusively on local color information, which made the approach sensitive to initial foreground and background labeling. The Connect's low resolution, coupled with poor synchronization between color and personal cameras, resulted in incorrect foreground and background labels that caused errors around edges. The team's improved image segmentation incorporates global and spatial information for helping to address this problem. First, a global foreground and background color model was established beforehand using multiple reference images and used for computing foreground and background probabilities given depth images. Next, a spatial smoothness constraint was added to encourage edges along pixels with the same color. The resulting image segmentation algorithm runs offline and couples depth and color information together with global and spatial information for a more robust segmentation with improved image quality along edges. The team has also implemented a pre-scanning method for constructing a detailed 3D static model of the office environment. Here our goal is to capture a 3D pre-scan of the room that can later be fused with live 3D capture data as people and objects move about the environment. Having a 3D scene reconstruction promises to enable more sophisticated 3D rendering. This 3D pre-scan process has the following steps. First, move the Connect around the room to capture the scene. Next, planar surfaces and image features are extracted from the captured depth and color images respectively. Next, image features and planes are matched between frames. Matching plane hypotheses are generated based on relative angles between each plane and matching image features. Having established a match between 2 frames, we then estimate the position and orientation that the camera was held using a method known as bundle adjustment. The use of both visual and planar features is particularly helpful in indoor environments. If visual features are sparse, then planar matching can be used. And in cluttered scenes where no planes are visible, image features can be used. And finally, build a 3D model. Each frame's depth pixels are then transformed using the estimated position and orientation and plotted in 3D space as a point cloud. The resulting 3D pre-scan captures a complete coverage of the room with up-close details that are both beyond the limited range of the depth-sensing cameras on the video wall display and free from interference that results from multiple overlapping depth cameras. The team's resulting video wall enhancements each incorporated depth information for enabling more natural one-on-one conversations. First, our image matting algorithm removed otherwise distracting visual artifacts by refining the segmented silhouette of foreground participants. And second, our 3D pre-scan method serves as a first step for enabling seamless eye contact during conversations using multi-perspective rendering.